Schütze ya se encuentra en la sala.
¿Qué tal?
Hola, buenos días.
Muy buenos días. Miguel ya está compartiendo el doctor Oliver su presentación.
Ok.
Oliver, por favor, ¿puedes abrir tu cámara y tu video, por favor? En la esquina inferior abajo y a la izquierda.
Ok.
Hola Miguel, me parece que tú le puedes prender el video y el sonido como moderador.
Creo que this is not in my hands, no está en mis manos, creo.
Ya,
Dice el sistema.
ya está, doctor Oliver, ya se encuentra. Nada más su video.
Ok.
El audio ya lo tenemos.
Miguel, ¿estamos listos para iniciar,
Listo.
por favor?
Sí, vamos a comenzar entonces. La siguiente plática plenaria es del doctor Oliver Schütze, del CINVESTAV-IPN. El nombre de la plática es Pareto Explorer, a Global Local Exploration Tool for the Numerical Treatment of Many Objective Optimization Problems. Les voy a decir una breve semblanza del Dr. Schultz. He is a full professor at the CINVESTAV-IPN in Mexico City. His research interests focus on numerical and evolutionary multi-objective optimization. He has won several international awards, including the AAA International Intelligence Society Outstanding Paper Awards of the Best Paper of the AAA Transactions on Evolutionary Computational Journal of in the years of 2010 and 2012, respectively. In 2018, he has held the Dr. Rodolfo Quintero Ramírez Chair at the Universidad Autónoma Metropolitana, Coajimalpa in Mexico City. He has co-authored of more of 150 publications, including 2 monographs and 5 textbooks and 12 edited books. He is founded on the International Workshop Series Numerical and Evolutionary Optimization. He is editor-in-chief of the journal Mathematical and Computation Applications and several member of the editorial board for Computation Optimization and Applications, Engineering Optimizations, and Mathematical Problems in Engineering. Dr. Schultz is member of the Mexican National Systems of the Research and the Mexican Academy of Science. Dr. Schultz, the microphone is all yours.
Okay, thanks a lot. Hi, everybody, wherever you are. I have to start with a stupid question. You hear me, right?
It's okay.
Okay, very good. So yeah, thank you for the introduction and for the invitation to the SNAIC. You guys made a great job. I mean, it's my first time at the SNAIC and I already feel home. Well, sorry for the joke. Yeah, today I'm going to talk about a topic, a class of optimization problems called many objective optimization, and about the Pareto Explorer, which is a tool to adequately address these problems. Yeah. So the outline of my talk is as follows. First, I will introduce to the problem, which is multi and many objective optimization problems. So now there are two classes of problems. Mathematically, they are identical. So that doesn't really matter from the mathematical viewpoint. It's the same definition, but we will see that from the practical point of view, it makes sense to come up with different methods for the treatment. And today I will talk in particular about two methods. This is the Pareto tracer for multi-objective problems and the Pareto explorer, which is the main topic of today for many objective problems. I will explain the Pareto tracer because we will need it for the realization of the Pareto explorer. Yeah, and finally, I will come up with two applications where many objective optimization problems arise and where the PE has been used to address the problem adequately. Good. Before I start, I have to say that I only have 30 minutes, so I cannot give you all the details. Just look at the figures and I will explain you the ideas. If you're interested in the details, here are three references, which are the core references of my talk. This is one paper on the Pareto tracer and two on the Pareto explorer. Second, I have to say that this is not all my work, but I did it together with collaborators. Here in particular, I have to mention Oliver Quatte, who has been my PhD student, who finished last year. And well, one star of his dissertation has been the Pareto explorer. Good, so let us start with the topic. And the topic is multi-objective optimization, but to introduce this, I start with classical optimization. So what happens if you have only one objective function? So for this, consider a very simplified example, makes it easier for me to describe, but already contains everything we need to know. Consider you have in your town, you have a vendor for vehicles, and this vendor only has three different vehicles. This is the Mustang, this is a Tsuru, and this is a bike, by whatever reason. You only have these three choices. Now, we make optimization. So what is the best vehicle? Well, it depends completely on what you want. So that's the first thing. We have to define the objective, right? So it is not clear what the best is. And so, for instance, we go for speed. And if we go for speed and we have these three choices, the Mustang is the winner, right? And all the others will not win. The Mustang is the best, the only best solution. Now, what about the cheapest vehicle? The cheapest vehicle out of these three is the bicycle, assuming that it's not a fancy bicycle and costs more than the Tsuru, right? So now I make the problem a bit harder, right? So I don't want to have, oh no, sorry, I still have another one. So what about the cheapest car, right? So maybe then it's the Tsuru is the winner. I mean, the cheapest car is also something we have in optimization, and this is constrained. So I can say, I would like to have the cheapest vehicle with a constraint that I have a roof because it rains in Mexico, right? And then here, the only winner is the Tsuru. But now we make the problem harder. So nobody buys always the fastest car or the cheapest car. I would like to have both. So I would like to optimize speed and cost at the same time. So now that I make the problem harder, let's look at winners, right? Let's compare, for instance, the Mustang and the Tsuru. The Mustang is faster, which is good according to speed, but it is more expensive, which is bad, right? So I cannot compare and can say that one of them is better according to both objectives, right? So it's the same with the Tsuru and the bicycle. Now the Tsuru is faster, but costs more money, right? So we cannot compare them. The same with the bicycle and the Mustang. So since I've made now the problem harder, and I have two objectives, right? The funny thing is I don't have one winner, I have three winners. All of them are winners. That's a funny thing, but it's a very, very common thing in multi-objective optimization. In multi-objective optimization, you don't expect one solution, but an entire set of solutions, which is the difference to classical optimization. Now, sorry, I have to bring some formulas, but don't look at the formulas. Just listen to my words and look at the figures. So in a multi-objective problem, I don't have one objective, I have K objective. Speed, cost, efficiency, whatever you want to have. So on the right side, we see an example where I have a one-dimensional problem, right? Here is X is only one dimension by whatever reason, and I have two objectives, F1 and F2. Right? And I would like to minimize both of them at the same time. So the most crucial thing is to understand what is a solution to this problem. Let's, for instance, look at this problem. This solution, or a candidate solution. It's not a solution, as we will see. So this candidate solution here, this is the value of X, is not optimal because, well, if I go a bit to the right, I will see I can decrease F1 as well as F2, right? So I can increase both functions at the same time. So I can build another car which is cheaper and faster. So this is not an optimal solution. This is also not an optimal solution. I go to the left and I can again improve all objective values. Now let's look at an optimal value. The optimal value, one optimal value is here. The graphs cross, but it is not important. It's just easier for me to show. Well, this is an optimal solution. Why? I mean, the thing is that locally I have two possibilities in a one-dimensional problem. I can look left and I can look right. Now let's look left. If I look left, I see that the red curve decreases, which is good. But at the same time, blue is getting higher, right? Which is bad. On the right-hand side, now blue decreases, but red increases, right? So in the neighborhood, I cannot say that any of these points is better according to the entire system than this solution. So that since there is nobody better, I have no choice. I have to call it a solution. So this is an optimal solution. If there is no other which is better, and better is defined in the case of dominance. Dominance means I find another point which is at least as good in all elements, and one of them is better. So the same cost but cheaper, for instance. So this would be a better solution. So now the characteristic is that this holds for this point, but if you see at this easy example, this holds for the entire set. All of these points have the characteristic I just told you. If I go left, one goes down and the other function goes up. And if I go to the other side, the opposite happens. So all of these points are, according to my definition, optimal, right? So this is the so-called Pareto set, right? It's a set of optimal solutions. Now, every point here has one objective value for F1, one for F2, up to F3, Fk. But if two objectives, we have this. So every point here has an objective value F1 and F2. Now we plot the entire set in so-called objective space. Here we plot F1 against F2. Right? And all these points here have an F1 and an F value, so F2 value. So every point here corresponds to a point here. So in this, the image of the Pareto set in objective space is called the Pareto front. And the Pareto front and the Pareto set are very important in multi-objective optimization. So the decision maker has a problem with K objectives and would like to know what to construct. And there is not one solution, there's an entire manifold of solutions. And it's even worse, there are not three solutions. So in general, for continuous problems, we can show, I will just mention this, is that the Pareto set is of dimension k-1. So that's very crucial. So you have a problem with K objectives. I'm the algorithm designer. So if you give me K objectives and I do a good job, I give you a manifold of dimension k-1. Right? So I will explain it a little bit, but more important is what this means, which I will address afterwards, right? So here are the optimality conditions for multi-objective optimization. It's not that important, but one thing or two things are important. If X is Pareto optimal, right, then the necessary condition is the following. Then there exists an alpha such that alpha is a convex weight. That means that all the alphas are non-negative, as well as that some of the alphas are 1. And the weighted sum of the gradients of the objectives are 0. So the 0 vector can be expressed as a convex combination of the gradients. Now, on the right-hand side, which I don't see because I see myself, unfortunately, we see such an example. Here is F1 against F2. So we see the Pareto front. We see an optimal solution in objective space. So this is a point on the Pareto front. And alpha, this convex weight, has a physical meaning. Alpha is orthogonal to the linearized Pareto front at the point f from x. This is an important feature I will mention 2-3 times in the following. It's not that important, but it's the basis for our method. Good. So now you can show, putting these things together, that the Pareto set is a manifold. As a comment, everything I say today is for unconstrained problem, which makes it easier for me, but all the messages in principle hold for constrained problem, makes it just more complicated. And if you're interested in this, well, read my papers, right? So you can put everything together, and then you will see that the Pareto set is contained in the 0 set of this function f tilde, right? So that you put the Karush-Kontaka conditions together, the necessary conditions, and you see all optimal solutions are contained in the 0 set. And then you use the implicit function theory, right? And just I tell you that you expect that the solution set under mild conditions is of dimension k-1. So well, important is you get K objectives, the solution set is of dimension k-1, right? And I would like to tell you what this means. So this slide is the slide you have to take home, right? Same stupid joke, I'm sorry. So if we have a B objective problem, it says follows. You see it on the left. We have F1 against F2, and I give you the approximation of the Pareto front, which we'll see here. So that could be two different cars or whatever. And you can always say, well, if you have this vehicle and you would like to change it to this vehicle, you see completely what it means. So if you change from A to B, the good thing is you will win. We wanted to minimize all objectives, this amount of F2, but on the same size, you increase F1, so you make a sacrifice. So if we have a B objective problem and I give you the Pareto front, you can always decide. I can never tell you which of these problems is the best solution. That depends on the problem, but you can make the decision-making process. You see what's going on. Now, it's in principle the same for three objective problems. There you have three objectives, you see these things and everything is fine, yeah, pay attention, it's three-dimensional. Now, if we have four objectives, I cannot plot four-dimensional. I mean, nobody can do this. So we have to do projections. And we see already that if we have these four objectives, right, that one point here corresponds. Well, these are the projections, sorry, I have to mention, this is F1 against F2 against F3, F4 is left out, then F3 is left out, F2 is left out, F1 is left out. So this is F2 against F3 against F4. So every point here corresponds to one point here, one here, one here, and one up, which I cannot show. So the same for B, and so the decision-making process is completely hard. So if we expect an object of dimension k-1, everything is fine for 2, 3, maybe even 4 objectives. But if we have a 100-dimensional or 100-objective problem, or even a 10-objective problem, we run into severe problems because we cannot compute the manifold. And even if we can compute the manifold, the trouble is that if I give this to you at 1 billion points, then I say you, which of these volume points do you prefer? I mean, there is no way to do this, right? So it's just too much. So that's why we select, though it's mathematically the same thing, we give different terminologies. We say that if we have 3, 4, or whatever you say, 5 objectives is a multi-objective problem, but everything else we call a many-objective problem because of the so-called curse of dimensionality. Okay. Good. Now coming to the tools to address this problem properly, I divided here roughly, and it's a bit oversimplification, into 3 classes. There are mathematical programming techniques, classical techniques, which basically compute 1 point, right? I will come back to this later. And then there are set-based methods, mainly evolutionary algorithms, which try to compute everything, a finite size approximation of everything. And then there are continuation methods by tactical reasons. I just put them separately because they are not 100% mathematical programming. They are not 100% set-based or heuristic-based, but they are kind of in between. This is the ones I think are very nice for multi-objective problems, right? So that's what I said already. All is not possible if we have 10 objectives. So what about 1? So is 1 fine? I mean, you say, well, why not 1? I mean, I'm not interested if I buy a car in buying a manifold of cars. I want 1 car, right? So this 1 car I would like to have, and I already put my specifications. I say the method what I want, and the method tells me this is your thing, which works. There are like 100 different methods for this. They work, but they have troubles, right? And I will explain it on the particular example of the reference point method. And here I take the easiest reference point method, but the problem holds for all scalarization methods, right? So assume you're building a bridge and your boss said he wants to, or she wants to have a bridge with this cost and this quality, right? And your boss is a bit greedy. This bridge with this quality and this cost doesn't exist. So you can make 2 things. And one thing is that you say, hey, boss, it doesn't work. It's correct, right? But it doesn't save your job, right? So maybe it's better that you do the best you could do. And the best you could do in terms of reference point is you compute the point which is closest to this. So here on the right, we see a hypothetical B objective problem, and we see a reference point. This is what your boss wants. So you can only compute the points which are here on the Pareto front or left, right up of this Pareto front. So you cannot compute points here, in particular, you cannot compute this guy. So you take the one which is closest to this guy. I mean, no, I cannot. I'm sorry, this part I cannot see, and if I go there, I see only myself. So we compute the closest point there. So that's the point. I mean, if you know more or less what you want, you can compute, you can tell it to the optimization problem and you get these points. But this is maybe a good starting point, but my message is that this is not necessarily the best point. In this particular case, if we use at reference point problems, the solution is unique, but the solution depends at least on 3 different factors. The first one is the reference point. I mean, how do you put the reference point if you want to build a bridge? I mean, yes, your boss told you something, but it could be also that your boss told you something and had no idea what the bridge is over an important road, right? If you change the reference point, you change the cost completely. And maybe you can save another 20% of the cost, which even your boss is interested in this, right? It changes, the solution is dependent on the distance and latest on the Pareto front. And the Pareto front is latest the one we don't know. So maybe the solution of such a problem is a good starting point, but my message is that you should not trust and say this is the solution, because we are dealing again with a high-dimensional manifold and you get something. And this something has to be explored, and that's exactly what the Pareto Explorer is doing, in particular for many objective problems. If you have 2 objectives, just compute it. But if you have 20 objectives, well, make the best out of it. And we think the best out of it could be to locally explore the solution around this point. And that's what we are doing in the following. And yeah, just a comment, this holds for all of these methods. For instance, the achievement scalar rising function, which is a better reference point method, but it's the same trouble, just it would take me 10 more minutes to explain everything. Good. So before I start, well, my message is if you can compute everything, do it. If not, use the Pareto Explorer. Now we are dealing with small problems that leading to the Pareto Tracer. And the Pareto Tracer is a continuation method. And the continuation method is described here. Don't look at the equations. It doesn't really matter. I mean, it can be formulated as a root finding problem. This root finding problem is transformed into an ODE, and then we solve the ODE. What you look is at this figure here. So this is the solution set. The solution set is given implicitly. We have a starting point. Now we would like to move along this curve of solutions. And what we do it in 2 steps. First, we linearize the manifold. This is the ODE thing. And then we project back. And then we do the same thing on and on and on. And that we get a sequence of points moving along this Pareto front. And I think that is locally the best you can do. Right. And this is already 50 years old. I didn't invent this, right? It was before my time. And even 20 years ago, there was a seminal work of Hillermeyer who said, well, now it sounds a bit too easy, but basically he said, yeah, let's use predictor corrector and use the Karush-Kontaka equations. So that's what he did. That is a good method, widely used, but it has 2 disadvantages. I will not go into detail, but one of them is that the 0 set is not in X space. So it's not about the design space. It is in X alpha space. Remember, alpha is the vector which is orthogonal to the linearized Pareto front. It's also called a Lagrange multiplier. So you have to look into this compound space. And where's the trouble? Well, here's one example. This is the Pareto set of a particular problem, but it's in X space and it's a line. And for predictor corrector methods, lines are the best to approximate because, I mean, you linearize, you have everything, right? So this is the easiest one. But if you live in X alpha space, right, as we have here, we see that the dimension increases, not the big problem, because if you 100 or 102 dimensions, who cares? But the nonlinearity of the problem increases, and here significantly. And this increases in many problems. So that's the idea of the Pareto tracer. The idea of this method is to separate X and alpha space whenever possible. I mean, for every X, there is an alpha. Just we separate them in the way that we treat X whenever it's possible alone and alpha whenever it's needed also, right? So that's the idea. And here I go in 4 slides over the idea, and you don't look at the equations. It doesn't really matter. So here is the idea. So we taken the method of Hillermeyer basically, and they said, where is X and alpha? We separated all these things. And the trick here was to say, I would like to steer in a certain direction in objective space. So once we choose the direction objective space, we could solve this system of equation and leading to this thing. But the question was still, which alpha do we choose? Or which direction do we choose? D, and D has to be chosen orthogonal to alpha, of course, right? So then we move tangential to the Pareto front. And here also don't look at the equations. Here is the theorem. Don't look at the theorem also, but I will explain you what the theorem says. The theorem says that every point which is regular, so some smoothness assumptions are fulfilled. For all of these points, we know the Pareto set, the tangent space of the Pareto set and the tangent space of the Pareto front. So it means nothing else that locally we know everything. Locally, it's like ODE formulation, so to say. So what does it mean? I mean, we are still in the same context of what I explained before. We have predictor, we have corrector. But before, what we had, or Hellermeyer was living in X alpha space, and now we are living only in X space, right? So we directly have the Pareto set, which really enhances the computational quality of these things. And just as I mentioned, well, everything what I explained now is the predictor, and as a corrector, we use the Newton method of Fliege and Zweiter with some adaptation, but it's basically this method. Okay, good. So this leads then to a new predictor corrector method, and I just shortly show 2 slides. The first slide is here a problem where we have 500 dimensions and an equality constraint, and we can solve in a perfect manner the entire Pareto set and front with using less than 1,000 function evolution, which is an amazing result, right? It's absolutely great. Their evolutionary algorithms will not even get warm, but I have to be honest. I mean, we have a local method, and it's just working locally. Here we have one connected component, and if we have this one connected component, we can compute it all. Pareto sets and fronts can have different connected components. We know this, and for these evolutionary algorithms are good, we hybridize them with evolutionary algorithms, right? But here I just explain the local part. So we can also do it for 3, 4, 5 objectives, as we see here, but we have the same curse of dimensionality. It's still the same problem. So if we have 10 objectives, we have a 9-dimensional manifold, which we have to approximate, so it doesn't really work. So that's why the Pareto Explorer comes into play, right? So the Pareto Explorer, don't look at the text again, look at this figure. It's a 2-stage approach. So in the first stage, you do what you can do so far. You take your favorite evolutionary algorithm, you take your favorite reference point method. Pardon?
5 minutes, please.
Oh, really? My watch says more. Okay, so we take this point and then we make a fine adjustment of this point, right? So that's what we are going to do. And how do we do this? I mean, for instance, we have, well, 2 classical ones is the steering and objective space. That steering and objective space says that I have a given point. This is my solution. I look at the objective value, and then the decision maker said, you know what, I would like to steer in this direction. But this direction, I mean, we can only have the direction if we know the Pareto front, which we don't know. But no, we know it locally, we know it. So what we could do is we can take a best fit approximation. So we have a point, we have a direction, and we steer along the Pareto front in a best fit direction because we have the Pareto front approximation locally, right? Yeah, here, this is how we realize it. The same thing in decision space. Here I have a Pareto set, and I would like to go left because my point X has the components 100, 1, and 2, and I would like to reduce the value of X1, right? Because the value of the product X1 is very expensive. I would like to do it. Here's exactly the same. I have the Pareto set in my hand. I use it locally. I move around this. Here, of course, it's a 1-dimensional plot. I mean, you have to think now 100-dimensional. That's up to you. The realization is absolutely the same with QR factorizations, right? But we use then basically the Pareto tracer for this because now we have a path of solutions. That is very important. So this was the steering and objective and a decision space. We have in total like 8 different variants. Now we can play, we can move to the knee direction. Oh, that is a funny thing. It looks completely horrible, but it's funny. We had to learn that the decision maker do not want to make changes in objective space, right? So they are in a certain niche. They want to keep in this niche. The Tsuru should be cheap. I mean, you can plug in a lot of things, but if the Tsuru costs the double, you take a Mazda and not a Tsuru anymore. So they want to make changes, so they have to react to the market. But in objective space, please, everything should be the same. I come up with an example for this. So this example is with a company from Germany. This is Kannegießer, and they are interested in designing laundry systems, right? I have no idea about this, but they told me that, you know what, I have these systems and they should be good in wiping away or washing away wool grease type A, wool grease type B, whatever that is. And then it's a long list of things up to cocoa. Yeah, okay, whatever. The 14th one, I understand, this is cost. Yeah, these I completely understand. So you make it good and you make it cheap. So now comes to the point where this is a cooperation with industry. I only can give you 4 parameters: the temperature, the amount of washing time, the frequency of the rotating unit. So we are only able to present a simplified model of this, but still the idea of the Pareto Explorer can be explained. For this, I will give you two different animations. To understand the animations, we look at the figure here. To this, I have to visualize a 15-dimensional objective vector, 14, sorry. So for this, we take the so-called Pareto wheel. So we take a unit circle and we divide it into 14 units. And in every unit, we normalize the values. So the closer the value is to the boundary, we have a good value, and the closer it is to the center, it's a bad value. So here is bad, here is good. So we have here the red one here, for instance, is something where we are bad according to the cost, but very good according to the quality. So now we use the Pareto Explorer where we steer, so to say, along the Pareto front, and we start with a high quality solution, and we would like to reduce the cost. So this is defined in objective space. dy is minus E14. So I see now the video left in decision variable space and y is in objective space. So we see that over time that the values are changing. Here I cannot tell too much, but I can tell here, as desired, the cost is going down. Well, this was a better value of cost, so basically we minimize minus cost. We don't minimize, oh yeah, we minimize the cost, sorry. And this is the one we do, and then we see changes here. But the changes could be whatever. I mean, the Pareto Explorer is exploring locally, and we cannot say this is the best solution. Now we have whatever, right? So then the company said, you're okay, well, what can I do? And then we said, yeah, we look a bit further. And then we had another video, and then they were really happy about this, right? So we've taken another time a high quality solution, which had also a large watching time. Now we can make the same steering and decision space. Now we said, let's remove X3, which is the washing time, leading to the following video. Yeah, here you see the video. You see the washing time reduces, and here you see basically nothing. I remember when my student came the first time, I said, oh, all these videos boring. And I said, this is until now my best video, because sometimes boring is the greatest thing of all. Because what do we see? We see that the washing time over the time evolution of our process reduces, and it reduces even by 50%, right? So this is important. But on the same time, in objective space, nothing happens. So that means that if you apply the method in this particular case, not in general, but in this particular case, we found a solution where the washing time could be basically halved, but the quality of the washing is essentially the same. So you can do the double in the same day, but for similar time, similar approximation quality. Good. So basically, I'm done. We did this on two. Pardon?
1 minute.
Yeah, 1 minute. We did this also in the case of plastic injection molding, where I don't go into details. I don't have the time anymore. Where you have to make it good and cheap and fast. We have identified 7 objectives, published several papers about this. But in principle, it's exactly the same. You take a point and you steer around. And basically now I'm done. Let me conclude. I presented 2 methods, the Pareto Tracer and the Pareto Explorer, for multi and many objective optimization problems. I have only presented the details, the underlying idea. Much more you can find in the webpage of my group. And we were doing much more, but the underlying idea will be always the same. Take a point, move in a certain direction. And we think this works in particular for many objective optimization problems. Yeah, and before I stop, give me 10 seconds to advertise the NEO. It's an online event. If you're interested in numerical and evolutionary optimization, the NEO might be interesting for you. Here is a figure from the glory days where we could meet in person, but I hope we will meet in person again in some years. But 2020, everything will be online. The event is November 18 and 19. It's too late to give a contributed talk, but you are more than welcome to attend passively. Okay, that's all from my side. Thank you.
Thanks, Dr. Schütze. We have questions. One question. What space is more suitable to provide information to Pareto Tracer? Decision space or objective space?
Which space is more important?
Okay, decision space or objective space?
Oh, well, that depends highly on the problem, but the Pareto Tracer is designed that it takes into account both, right? So we discretize the set, and we have means to discretize the set in decision space if it's important, Or, and I think this is more important in objective space, because in objective space, that is what you get, right? You get a car with 300 kilometers per hour, right? So you don't really care about all the other details if you care for a high quality car. So I would say objective space, but both spaces are very important.
Okay, thanks. Another question. It is a talk very interesting. My question is, are there other available tools like to you have exposed?
If I have developed other tools? Oh, that's
Okay.
my job. Yeah, I
Yes.
have 30 tools, 50 tools, I would say. Today, I only made advertising for the Pareto Explorer, which, well, I need the Pareto Tracer, but the Pareto Tracer I only explained to the detail that we could understand the Pareto Explorer. But yes, yeah, I have, look at my homepage, I have 50 more tools.
Okay, that's the answer, Rocio. I have a question. It's very interesting that your tool or your tools, mathematical tools, improving to the Pareto front, and I imagine a wavefront in optics.
Yeah.
For our optics application,
Yeah.
to optical demodulation in interferometry, to use the Pareto from same of the optical wavefront of the interference.
Okay.
Maybe results a good maybe have a good results if you use this application. Well, I am optics.
Yeah, no, it's fine. I mean, I'm always I'm personally an algorithm designer, so I design algorithms. But my challenge is to apply it to problems. I have several applications, but in all these applications, I'm just the guy who understands the problem as much as to get it and then to solve it together with the practitioner. And I'm very interested in applying it to optics.
Yes, it's very interesting, this application of Pareto front. Thank you very much, Dr. Oliver Schütze, and
Oh, thank you. Thank
this
you.
talk, very interesting. Thanks. Bueno, los invitamos a todos a continuar con nuestras sesiones. Vamos a tener un receso. El receso es de 10:20 a 10:30. Se les recuerda que al terminar el receso a las 10:30 tendremos otro